All right, for the first warm-up question, we're being asked to find the magnitude and direction angle. So it's just to get you going with these things, make sure that you're good to go. So just figure out this lovely magnitude here. So the magnitude is just going to be 1 squared plus the square root of 3 squared. So this is the square root of 4, so this is 2, which we might have recognized, especially if we had graphed this. We're going over 1 and up square root of 3. So this is a special right triangle, so I know that that angle right there is going to be pi over 3, or 60 degrees. So that's going to be my direction angle. Number 2 for the unit vector of 3, 3. We're first just going to find the length of the vector. So that's just going to be square root of 3 squared plus 3 squared. So that's square root of 18, which is 3 rad 2. And so unit vector, we just divide each part by that length, which we can simplify, right? We'll get 1 over the square root of 2, 1 over the square root of 2, and I can just rationalize that. Now, here's another way we could look at this, same as kind of up there. We could recognize that this is a 45, 45, 90 right triangle, and so this is just going to be 3 rad 2, and then whatever the sine and cosine values of the special angle would be are exactly what we would have here. So this would be cosine of 45, which is the square root of 2 over 2, and this would be sine of 45, which is the square root of 2 over 2. Just another way of looking at it. Warm-up 3, find new magnitude, length 7 in the direction of 5, 12. So first thing I want to do is just find the length of this. So I'm recognizing this is a 5, 12, 13 right triangle, or I would actually do the workout to figure out what it is. I want to find the unit vector. So remember that is we just divide by its current length. And then I just multiply by the new length I want. So this vector w needs to have a length of 7, so I'll just multiply the unit vector v by 7. So I end up getting 35 over 13 and 84 over 13. Donezo. Number 4, we want the magnitude to equal 7, and we want it to go in the direction of y equals x. So I'm just going to grab the slope of this, so that's 1 over 1, and I can turn that into a vector. So this vector is capturing the slope of 1, which is the direction of y equals x. And I want it to have a magnitude of 7. So I need to first turn this into the unit vector. So I'm going to just divide by its length, and I will actually rationalize all at the same time. And then I just need to multiply this by 7. So I get 7 rad 2 over 2, 7 rad 2 over 2. Ta-da! Math. Before we get into the application questions, I just wanted to remind you kind of visually what vector addition is doing. So here I have this red vector is representing the velocity of the water, and I have this blue vector is representing the velocity of like a boat or something like that. So if I kind of line them up on top of each other like that, so that both of their tails are in the same spot, the resulting vector always falls in between them. Okay, so in between the smaller side of the angle, no matter what I make this. So if I make this something like, that, the green vector, which is right there, is going to always fall in between them, no matter what I make the angle. All right, so I'm just kind of showing you a couple different examples here as I change the angle, that the green vector is always between the red and the blue vector. So the resulting vector always kind of falls in between the interior angle, which is the angle that's less than 180, not the exterior, which is the angle that's bigger than 180. So let me bring that back here and just want to show you kind of a visualization of what's happening here, where this green vector actually falls. So if I take the red vector, and it doesn't matter if I use the blue or the red one, and I move it to the head of the blue vector, you can see that the green one goes from the tail of the blue to the head of the red. And it doesn't matter what way I do that. So let's change it here, and I'll just kind of flip-flop this. So now it's going from the tail of the red to the head of the blue, and that is how vector addition works. No matter what's happening. So let me, again, change the angles here, make these something, a little bit more entertaining for us. That's not a great one. Ew, I hate that one too. Whatever. We'll do this one. So if I do the resulting vector of this, same idea. If I just line them up, it always ends up that they meet up. So questions that we're about to be doing are going to be asking us some variations on these things. So some might be that we know everything about the water or the wind. Okay, so we know its magnitude, we know its direction. Maybe we know everything about the boat, so we know its magnitude and its direction, and then we'd be asked to find everything about the resulting vector, okay, which is which way this boat would actually go if we were to allow it to move through the water. Or maybe we have something that's a little bit different than that. So maybe we know that we want the green vector to be going east. So we need to figure out, like, if this is what the water or the wind is doing, which way does this boat need to point itself to make sure that the actual boat travels sideways. So things like that. So I'm going to do one where I'm going to make sure the boat travels straight down, and I'm going to actually, here's our boat traveling straight down through the screen. Wow, it's amazing. So I hope you kind of get the visualization of what's happening here so that it will make the next part a little bit easier. So one of the big things that we use vectors for in real life applications is to capture the velocity vector. In real life applications, we can actually use position as a vector, velocity, acceleration. Like, those are really the physics applications that you would be using vectors in at first. And I've used them in programming as well. When you're trying to make a physics engine for a game or something like that, we're always using position, velocity, and acceleration as vectors. So basically, velocity is a vector because it has a magnitude, aka the speed, and then a direction, so which way you're actually going. So for this first example, we have an airplane. It's going at a bearing of 170 degrees, and its airspeed is 460 miles per hour. So there's a difference between airspeed and ground speed. Airspeed is just what the plane does by itself, as if there was no wind whatsoever in the world, and then ground speed is kind of the resulting vector when you include wind and things like that. So this is just airspeed. So first thing I want to do is just get like a nice visual of where this is. So if I have a bearing of 170, remember that bearings start from up here and they go clockwise. So 170 is going to be like right here-ish, where there's there's exactly 10 degrees right there. Now, when we want to write a vector for this, we're going to use that magnitude cosine theta, magnitude sine theta. But this theta right here is the direction angle theta. So I need to figure out what is that angle there. So if I start here, this is 90, 180, 270, plus an extra 10. So that's going to be 280 degrees. And then that magnitude is the airspeed. So I can do 460 cosine 280 degrees, 460 sine 280 degrees. All right, so the first example we're actually going to get into here where we use these vectors is actually kind of the harder example. So we're actually starting off harder, and then this next example after this one will be easier. But we have someone flying an airplane leaving Westchester Airport. They're flying a Boeing 727, which is the name of the airplane. So that 727 is useless information to you. So just cross it off, basically. And they're flying east. So that's really important for us. That's what this is going to be. The actual plane needs to be flying east. So I'm just going to represent that by a blue vector right there. Now, they tell us that there's a wind going 65 miles per hour with a bearing of 60. So I'm going to start up here, bearing of 60. And I'm going to label the direction angle. So I personally never label my drawings with bearings because I don't want to get confused with what they are. I'm just going to label this one with the direction angle. So here's a little vector that represents the wind, and I'll sometimes write how fast it's going right at the arrowhead so that I don't have to read the problem again. And then, let's see, it says the plane has an airspeed with no wind, 450 miles per hour. So we have this plane over here, and we need to figure out where it's going to be. So this is the way we want to go, and the wind's going to be pushing us up. So if the wind is kind of pushing us upwards, then our plane actually needs to kind of point itself down a little bit so that when the wind hits it, it will push it to end up going directly east like that. So I don't actually know this angle right here, but I do know that this is going 450 miles per hour because that's its airspeed. So from this, I can write an equation. So I know that the plane plus the wind will equal this resulting vector over here. Okay? So plane, I can write some of the things right now. So I can write 450 cosine theta. I don't actually know theta yet. 450 sine theta. I'm going to kind of switch to vertical because it's a little easier to see this when we go vertical. So that was the plane. Now I'll do the wind. The wind I know everything about. So 65 cosine 30, 65 sine 30. And I know that if I add those together, it will give me this resulting vector. Now, the resulting vector, I know its direction angle is 0. So when I do cosine of 0, that's going to be 1, and sine of 0, that's going to be 0. So I know this value is 0. And this one, I don't know how fast the plane is actually going. I don't know its ground speed because I haven't calculated when I combine these things what's going to happen. So right now, this is an unknown value. And when I'm looking at these, I know that I can just add the x values together, and that will give me the new x value, add the y values, and that gives me the new y values. So if I'm looking at these, there's two unknowns, theta and x. So I can't work with that one yet. So I need to work with a different one, which is going to be this one here. So I can make a little mini equation out of this and say, all right, 450 sine theta plus 65 sine 30 has to equal 0. And now I can find theta because there's only one unknown. Right, so let's do that work right here. I'm kind of running out of room. Poor board management here. So I got 450 sine theta equals negative 65 sine 30. And I'll just divide that by the 450 there to kind of make life easier for us here. And I'm just going to do sine inverse of this. And I'll get theta is negative 4.14. Okay? So what I need to do is figure out what the actual angle is, and as a bearing I mean. So right now this is a reference angle. So I know that the actual bearing is going to come from north all the way around. So I'm actually just going to say that theta as a bearing, well, that's going to be 90 plus positive 4.14. Okay, because I need to be coming from north all the way through. So 90 plus that theta value as an absolute value of theta. I don't care that it's negative. So that's going to be my bearing, 94.14. And that's the first part of this. The second part is we need to figure out how fast it's actually going. So I'm going to do that up in this kind of corner region because, again, poor board management. But I'm going to use this equation way over here. But I have a problem. That theta as a reference angle, I need to be really careful about plugging it over here because this is theta as a direction angle, not a reference angle or a bearing. So I'm kind of in luck that negative 4.14 actually works in this case because I could go this way or this way. So it could be 356 degrees, or it could be negative 4.14. So it just kind of worked because of the quadrant we're in, that I can use negative 4.14. If I was in a different quadrant, I would probably go about actually figuring out what the true direction angle is as a positive value. So now I'm just going to plug these things in. So 450 cosine of that negative 4.14, that's a 4 and it's negative. And I would have stored this value in my calculator so I'm exact. And then I just add this with the 65 cosine 30. And whatever this equals, when I add these things all together, can't see my answer key, is the true ground speed or actual speed. So that's going to be 505.12 miles per hour. And that is the harder question. I'm actually going to do the next question with you as well because this is the easier version of it. So start off by just setting up. Here's our our plane, which is going to be based off of the air, and I can add that to the wind, and that's going to equal the result, which is either the, oh boy, words, ground, what I sometimes refer to this one as the actual, because that's what's actually happening, how fast it's actually moving. So in this case, they tell us the plane is going at a bearing of 170, 460. So bearing of 170, that's going to leave me 10 right there, going at 460. So I can write the plane right now. Plane is going to be 460. I need to use its direction angle. So I'm going to use 280. You could also use negative 80, because that would be this angle. I just tend to use positive ones. It's really important. We're not using the bearing. You'll get every question wrong if you put a bearing in there. Gotta be direction. All right, so there's my plane. Next comes the wind. So they tell us the wind is blowing at a bearing of 200 at 80. So from here, that's going to be 90, 180. So 200 is going to be somewhere right here. There's 80. And what I really want is this, okay? So if I went from here, this is 90, 180. This would be 270. I'm 20 less than that. So its actual angle is going to be 250. That's its direction angle. So wind, I can write 80 cosine 250 and 80 sine 250. So because I know everything about these now, what it's going to do when I just add these together is it's going to give me this result, meaning I don't actually need to do a whole lot of work to figure it out. So I'm just going to directly in my calculator do 450 cosine 280 plus 80 cosine 250 carefully, because those numbers tend to like blur together. And I get 52.52, and I'll do the same thing here, and I get negative 528.19. So that's the component form of this thing right here. I can see it's positive x, negative y, so I know that it's going to be somewhere down here in the fourth quadrant. So to find the actual ground speed, or the speed of this resulting plane, I'm just going to do that squared plus that squared and square root. So I would have had stored these in my calculator, okay, and would do the exact values. So there's no rounding. We can't round here or bad things happen, okay? That's when like space shuttles blow up and crazy things happen. No rounding. So I just used exact stored values in the calculator and got that resulting vector. Next, I want to find this theta reference angle right here. So I'm just going to use tan inverse on this. So I'm going to say theta equals tan inverse of the y over x, so negative 528.19. And again, I'm storing these values. So these are the exact values, not these decimals that I'm writing down right now. And I got that this is approximately negative 84.32. So 8432. And I know that this is in quadrant 4, and I want this to be a bearing. So this part's 90 and that part's theta. So I'm just going to do 90 plus 84.32, and that's going to equal the bearing that the plane is actually going in. So that's the ground direction, and this is the ground speed. So this is the easier version, because you were given everything about the plane and everything about the wind, and you just have to basically find an xy for the component and then find its result and its direction angle slash bearing, which is a little bit easier than the other one where we had to first find theta and then find the speed.